Hi guys! In this video, I'll be talking about the fundamental theorem of calculus. The theorem has two parts. In the first part, we will learn that the integral and derivative are inverse processes of each other. In the second part, we will learn how to solve definite integrals without using the limit of Riemann sum. So somehow, this theorem gives us a better or a faster way of calculating integrals, definite integrals. So let's get started. So first, we recall the definition of antiderivatives. A function capital F is called an antiderivative if of a small function f if the derivative of the capital F is equal to the small function f. And in here, we are talking about on a given domain or on a given interval. Okay, so function capital F is called an antiderivative of a function small f on an interval I if capital F prime of x equals small f of x for all x inside the interval I. Now, if we are given a small function f of x, then the derivative of that small function of f is denoted as small f prime of x. Okay, derivative of f is small f prime of x. Now, the antiderivative of small f, this is another function which we will denote by capital F, satisfying the equation capital F prime of x equals f of x. Okay, so I hope we remember this one from our calculus 1. So, what is the first part of the fundamental theorem of calculus? If small f is continuous on the interval AB, closed interval AB, then the function capital F, which we will define this way, look at this definition, for all x between A and B, that function is continuous on the closed interval AB. Okay? So we have a small function f which is continuous on the closed interval AB. Then the function capital F, which is defined this way, is continuous on the closed interval AB. Furthermore, this function is differentiable on the open interval AB, and its derivative is actually equal to small f of x. Okay? So again, in here we have a small function f of f which is continuous on the interval AB, closed interval AB. We define the capital F this way. Then this function is continuous on AB and differentiable on the open interval AB, and its derivative is equal to small f of x. Now, let me just analyze this function capital F. Look at this function. Its variable is x. So, the function capital F has the variable x. On the right hand side, if you look at this, the x here is actually related to this upper limit of integration. Okay, that's the upper limit of integration. The lower limit of integration here, this is constant. Lower limit of integration, it's a number, it's a constant. Okay? And then, if we look at the integrand, particularly the variable of your integration, look at this, that's different from the variable x, different from the variable of capital F. Okay, the variable of capital F, that's your x. And that x is related to this upper limit of integration. Okay, so in this definition, I want to emphasize that the variable of your integration, the variable that you see in the integrand, is not the same as the variable of that capital F. Okay? And again, since you are doing this whole thing here, looks like this is a definite integral, the variable of integration here can be replaced with another letter or another variable, except, of course, by x. Okay? So, that's the fundamental theorem of calculus part 1. But let us see how this one works. So, if your capital F is defined this way, the derivative of that capital F will be equal to small f. This small f here. This small f here. And recall from the previous slide, this definition, this means that capital F is actually an antiderivative of small f because it satisfies the condition capital F prime of x equals small f of x. So capital F is actually an antiderivative of small f. So if we are given a function small f, then we have a way of finding an antiderivative immediately by doing this definition or doing this expression. Okay? Furthermore, if we look at this way, we look at this f, capital F prime of x equals small f of x, we can rewrite it this way. If your small f is continuous on the closed interval AB, then small f of x can actually be written as the derivative with respect to x of this expression here. Derivative with respect to x of the integral from a to x of f of t dt for all x inside the open interval AB. Okay? So now, in here, what you see is that this part here is integration, and then you are getting the derivative. Okay? So what we actually have is a derivative of an integral. So this one here is derivative. So what we actually have is the derivative of an integral Okay? Derivative of the integral of f, it gives us f. This is f here. We integrate that and we get the derivative again. We are able to get f again. So the derivative cancels the effect of an integral. Okay? The derivative cancels the effect of an integral. So let us show how it can be used via examples here. These are just easy examples because what we're going to do here is just to find the derivative of the given functions. And we need to apply chain rule whenever necessary. Because again, if you look at this is x only. The upper limit of integration is simple x. So if this part here is different, it's not just simple x, then we have to apply chain rule when getting the derivative. Furthermore, this is an upper limit of integration and the lower limit of integration is constant. So if both of them, this expression here is in terms of x, the lower limit of integration is also in terms of x, then we need to apply some properties of definite integrals. Or if the upper limit of integration is constant and the lower limit of integration is a function in terms of x, then we need to apply properties of definite integrals. Okay? So, for the first one here, we want to find the derivative of g of x. This is our g of x. So if we get the derivative of g of x, g prime of x will be equal to, if you look at this, lower limit of integration is constant, the upper limit of integration is just a simple x. The fundamental theorem of calculus part 1 says that you just need to copy the integrand. Just need to copy this integrand. If you look at this, let's go back. Capital F of x in here, small f of t in here. We get the derivative of capital F. We just need to copy small f of f. F of x. Of course, don't forget that we are going to replace that dummy variable there with the x in here. So, this one, g prime of x will just be square root of 1 plus x cubed. Right? For number 2, we want to find the derivative with respect to x of the integral from negative pi over 4 to x cubed of tangent t dt. So notice in here, the upper limit of integration is x cubed. The lower limit of integration is constant. So we don't have a problem with the lower limit of integration. But we need to make sure that the integrand is continuous. Let me just take a note on that. Integrand, let's put the specific integrand here. Tangent t must be continuous on the interval negative pi over 4 to x cubed. Take note that the tangent function, it has infinitely many discontinuities. So in here, to be sure that the tangent function is continuous on this interval here, we'll just assume that x cubed is less than pi over 2. And of course, greater than or equal to negative pi over 4. So let us also put that one. So the x cubed is less than pi over 2 can be greater than or equal to negative pi over 4. So we will assume that one so that we can apply the fundamental theorem of calculus part 1. Therefore, if we do that, we have the derivative with respect to x of the integral negative pi over 4 to x cubed tangent t dt. This will be, first, we will copy the integrand here and replace the t with what's on top in here. So this will be equal to tangent x cubed. But since this is x cubed, we need to apply chain rule. We need to multiply this expression here by the derivative of x cubed. So times 3x squared. So this will be the derivative of the integral from negative pi over 4 to x cubed of tangent t dt. Okay? Finally, for number 3, notice that in this problem, the lower limit of integration is a function of x. The upper limit of integration is constant. But in the fundamental theorem of calculus, the upper limit of integration must be the one that is in terms of x, and the lower limit of integration must be the constant. So we have to find a way to switch these two limits of integration. And from the definition of the definite integral, when you switch limits of integration, you have to take out a negative. This means that your y equals the integral of sine x up to 1 of square root of 1 plus x squared, 1 plus s squared ds can be written as negative integral from 1 up to sine x of square root of 1 plus s squared ds. So now, the upper limit of integration is a function of x, while the lower limit of integration is a constant. So upper limit of integration is a function of x, the lower limit of integration is constant. So we can apply the fundamental theorem of calculus on this part. And of course, we also apply chain rule. Now, I just want to emphasize again the continuity of the integrand on the given interval. In here, if you look at this, let me go back to this one. We have 1 plus t cubed. Our lower limit of integral is 0. And our upper limit of integral is x. But we have square root in here. So you got here 1 plus t cubed, but you take the square root in here. So we need our x to be such that this expression here is positive. I did not emphasize that in number 1, although I have emphasized it in number 2. Similarly, for this item number 3. Now, in item number 3, we don't have a problem actually. The reason is, even if your sine x can become negative for whatever x you have, you do s squared, which will make it positive or 0. And then you add 1, which means this expression here, the one inside square root, is always positive. So if you take the square root, we don't have any problem. So we don't need to do some restrictions on the x in this part. But for number 1, we actually need to do some restriction. Okay, we actually need to do some restriction. Anyway, so since we already have our y this way, written this way, we can now find y prime to be, we still have that negative, and then this is our integrand. We will replace the s here with that upper limit of integration. So that will be square root of 1 plus sine squared x. But by chain rule, we need to get the derivative of sine x, which means we multiply this expression by cosine x. So this will be the final answer. So that's the first part of the fundamental theorem of calculus. Oh, by the way, if you are reading other references, my first part of the fundamental theorem of calculus may not be the first part of the fundamental theorem of calculus in other references. And my second part may not be the second part in other references. But still, they will do the same thing. In fact, if you found a reference um, that states the combined form of the fundamental theorem of calculus, then it would be nicer. I mean, the first part and the second part says that they are just the same thing. Meaning, the first part, if you think, if you assume the first part, the second part will be implied. And conversely, if you assume the second part, the first part will be implied. So it means they're just the same thing. Now, for the second part, if small f is continuous on the closed interval AB, and capital F is any, take note of this, any antiderivative of small f on the interval AB. Because it's an antiderivative, it means capital F prime of x is equal to small f of x. Then, the definite integral of f of x dx from a to b. Take note of the upper and lower limits of integration. Those are just the endpoints of your interval. So the definite integral of small f of x dx from a to b, this can be obtained by doing this substitution. Capital F of b minus capital F of a. So we evaluate the antiderivative at b minus the antiderivative at a. So now, if we want to evaluate definite integral, all we need to know is to find an antiderivative. All we need to do is to find an antiderivative. And once you have your antiderivative for your small f, then just evaluate it. So it's much faster in a sense than doing the limits of Riemann sum. Now, you may take any antiderivative of small f. So if you look at this, f is any antiderivative of small f. The reason is, if you took another antiderivative, then it's just, it's just the original antiderivative plus a constant. Since capital F is an antiderivative of small f, and c is any constant, then capital F of x plus c is also an antiderivative of small f. If you do this expression here, on the right hand side, the plus c will just remain plus c. And you do your subtraction here, which means that this c minus this c, it's just equal to 0. So what's left is capital F of B minus capital F of A. So in short, we can always take the antiderivative for which the constant c is equal to 0. Okay? So let us practice this method. We want to evaluate the integral from 1 up to 4 of e to the x dx. Take note that if you get the derivative of e to the x, it's also e to the x. So the antiderivative of e to the x is still e to the x. So this one will be equal to e to the 4 minus e to the 1, or e to the 4 minus e. Easy peasy. Now, let me just go back to this expression here. This one, you can actually rewrite this as capital F of x evaluated from x equals a to x equals b. This means that, well, in order to find the definite integral, you actually need to find this one first. A lot of times, I'll be doing this one before doing this one. Okay? Another problem here. Find the area under the curve of y equals x squared over the interval negative 2, 1. So in here, find the area under the curve. If we consider the graph of y equals x squared, it will be something like this. And since we're only considering the interval negative 2 to 1, then we can chop the graph up to this point. So this is negative 2, this is positive 1. Area under the curve, like what I've mentioned before, under the curve, it means it's actually the curve between the curve and the x-axis, which means this is the region that we are interested in. But as one of the remarks, when we define the definite integral, the area under the curve is just the definite integral. From negative 2 to 1 of x squared dx. So, first, the antiderivative of x squared. The antiderivative of x squared, this is x cubed over 3. You evaluate this from x equals negative 2 to x equals positive 1. In here, if we know which variable we are evaluating, we don't have to put this one here and this one here. You can just write it as, so let me just write it here, or x cubed over 3 evaluated from negative 2 to positive 1. Since we already know that we are just evaluating the variable x. So this is the upper limit of integration here. This is the lower limit of integration. So we evaluate the antiderivative at the upper limit of integration minus we evaluate the antiderivative at the lower limit of integration. So this one is just 1 cube over 3 minus negative 2 cube over 3. So if we simplify this, this is 1/3 minus negative 2 cube, that's negative 8. So we have negative 8 over 3, but we got here negative and negative, so it becomes positive. So 1/3 plus 8/3, this is equal to 9 over 3, which is equal to 3. So that is the area under the curve of y equals x squared over the interval negative 2, 1. Okay? So now, calculating definite integral is much faster than doing the limits of Riemann sum. Besides, when doing the limits of Riemann sum, sometimes there are integrands which we cannot sum up, or there's no formula for the summation. If the integrand is just linear, constant, or quadratic, then it's possible to do limits of Riemann sum. Otherwise, it might be harder. Now, let's look at some more examples. We want to find h prime of x. We want to find h prime of x if h of x is this way. If you look at this, the upper limit of integration is x. The lower limit of integration is square root of x. Both upper and lower limits of integration are in terms of x. And we want to find h prime of x. However, if we do that, if we want to do the fundamental theorem of calculus, or if we want to use the fundamental theorem of calculus, one of the limits of integration, this or this, must be a constant. Therefore, we cannot apply directly the first part of the fundamental theorem of calculus here. So what we're gonna do is to separate, or to divide this into two parts. Take note that in here you got x squared. Denominator is c to the 4 plus 1. The denominator will never be equal to 0. Which means this function is continuous everywhere. So if that is continuous everywhere, we can choose any constant, because there will be no problem on the interval. Okay? So in here, we will have, let us choose x equals 0. We can rewrite this as square root of x up to 0 of z squared over z to the 4 plus 1 dz plus integral from 0 to x of z squared over z to the 4 plus 1 dz. Remember this one? If you got the integral from a to b, this is integral from a to c plus integral from c to b. Okay? So that's what we did in here. Furthermore, in here, lower limit of integration is in terms of x. In here, upper limit of integration is constant. We have to flip it. So this one can now be written as negative integral from 0 to square root of x z squared over z to the 4 plus 1 dz plus integral from 0 to x of z squared over z to the 4 plus 1 dz. Now we are ready to find h prime of x using the fundamental theorem of calculus 1. We have negative. Then for this one, we got that negative. Then we replace this z here with square root of x. So for emphasis, I'll just write it as square root of x squared, square root of x squared over square root of x to the 4 plus 1. Then by chain rule, we need to multiply by the derivative of square root of x. That will be 1 over 2 square root of x. So this is this guy after derivative. Then the other one plus, this is simple x only. So we just replace the z here with just x. So plus x squared over x to the 4 plus 1. So this is the derivative of h. Okay? So for the last example, I will leave this to you as a homework. So for which values of x does the function, this expression here, attain its local maximum or its local minimum? Remember from Cal 1, when we want to do local maximum or local minimum, we can do it by getting the critical numbers of your function. Finding the critical numbers is by using the derivative of the function. So this one here, this is just your function, and it is in terms of integral, definite integral. You need to get the derivative of the function by using the by using the fundamental theorem of calculus 1. And then from there, you find your critical number. After getting the critical numbers, you test which one has the local maximum, which is the local maximum, or which has the local minimum. Okay? Now, as a final remark, remember that I mentioned the first fundamental theorem of calculus tells us that, well, as a whole, the fundamental theorem of calculus tells us that derivative and integral are inverse processes of each other. So if you look at this, the derivative of an integral, it gives back our original function. Okay? It gives back our original function. But what about the integral of the derivative? The integral of the derivative. Well, we already have seen it when we defined the antiderivatives in Cal 1 or from Cal 1. Oh, not really the antiderivatives, but the indefinite integral. This is what we know. The integral of f of x dx. If capital F is an antiderivative of small f, then capital F prime of x is equal to small f of x. Furthermore, Furthermore, capital F of x plus c, this is your integral of small f of x dx. Correct? If you integrate a function, you are actually getting the general antiderivative. But then again, your f of x, capital F of x here, is an antiderivative of small f of x, and it follows this expression. So if we replace the small f of x here with capital F prime of x dx, notice this one now is integral of this expression, which is a derivative. Integral of the derivative, and it gives back our capital F. So integral of the derivative of capital F, it gives back our capital F. However, it gives us a family. Not just our capital F, but a family of functions. So indeed, the fundamental theorem of calculus tells us that derivatives and integrals are inverse processes of each other. So that's all for this lecture. Have a great day.